Okay, please take your seats. We have a couple of announcements. Quiz 1 is 1.5 weeks away. There's an announcement handout that's on top over there and over here that basically gives sort of the outline. It's a closed book exam, but you are allowed to bring a crib sheet. Okay, so I invite you to look at the announcement, and if there are any questions, we can talk about it on Wednesday. We are going to be sending out a final exam questionnaire. When, George?
I don't know.
Tomorrow. Okay, by tomorrow, by email, trying to find out when are good slots for having the final exam. Unfortunately, some confusion among, we're not sure which parties, resulted in us not having our exam scheduled. So we have to get it scheduled, and we have to minimize the number of conflicts. Also on Quiz 1, if you have a conflict for some reason with Quiz 1, please talk to your recitation instructor. Let's see, problem set 4 is available at noon. That's just after class. This is a short problem set. It's due on Friday. I'm sorry I couldn't give you a weekend for it. Basically, you know, with all of the things that happened, we ended up getting things slipped because of the week of September 11th and all, and then at some point we have to pay the piper. So I've made this problem set a little bit light. The first problem you can get going on today. The main reason to have it due on Friday is so that I can get it back to you graded before the exam. Okay, so the grader is going to be working all weekend to get this graded so that it can be available on Monday, is that right? Or Tuesday? Tuesday, I believe, they'll have it ready. They'll have it graded by noon on Tuesday. Okay, and the exam is on Wednesday. So you can review your understandings on that material. So any questions about this basic administrivia? Okay. So today we're going to start talking about hashing, which I think probably most of you have seen in one guise or another. If not, you'll know it pretty soon. And it basically comes from a very common problem that arises in compilers and in a variety of other things where you have a table of symbols and you want to store them efficiently so that you can look them up. That's called the symbol table problem. Okay, so we have a table T holding n records. Okay, and a record is just a hunk of data. It's broken into what are called fields. So each of those is a field. And generally, we're given some pointer to the record, some pointer x. And one of the fields is designated as the key, okay, which we denote key of x. And all the others just have to be carried around with it. This is satellite data. Okay, so this is a record. And the idea is to make a table of a bunch of records to support a collection of what are called dynamic set operations. So dynamic set is a set whose elements change with time. So it's not a static set, which we're used to thinking of in the mathematical sense. And typically, dynamic sets support two operations, insert and delete. So the operations here are insert an element x into the table, delete a record T from the table, and search the table for given key value, K. And what it does is this returns a record X such that key of X is equal to K. Okay? And so these two things make it a dynamic set. okay, because it's changing. So any set that supports insert and delete, we call a dynamic set. We've seen one dynamic set before this. Does anybody remember what that set was? Yeah. Priority queue, using a heap data structure to support priority queue operations. And there it was dynamic because we had insert and extract min or extract max, depending upon whether it was a min heap or a max heap. Okay? So here's another example of a dynamic set. So before we get to hashing, let's talk about a really simple way of implementing this, which sort of leads to hashing. Okay? So a very simple but elegant idea. And in fact, I've seen times where people were proposing way more complicated data structures for things when the data structure that I'm going to show you works perfectly well. Okay? So suppose the set of keys is capital K, which is a subset of 0, 1 to m minus 1. Okay? And that the keys are all distinct. So only one key occurs at a time. Okay? You never have two. It's a true set. Okay? Often we'll talk about dynamic sets where it's really a multi-set, where I could have two different records, so the same record will only be included, but we may have more than the same key repeated. So what I'm looking at for the moment is just a situation where the keys are distinct. Okay? So they're all different records, but we're going to have keys being distinct. And so what we do to support this is a very simple structure. We just simply set up an array T going from 0 to m minus 1. Okay? And we store the elements in the table T where the kth slot of T is equal to x if x is in the key set and the key of x equals k, and it's equal to nil, in other words, an empty slot, otherwise. Okay? This is called a direct access table. Okay? And how can these operations, how much time does it take to support these operations in a direct access table? Constant time, right. Okay, it's really trivial, right? I mean, you take an element and you look at its key and you stuff it into that slot, and you know it's the only one. Okay? And if you want to find out if a key is in there, you just check the slot. If it's in there, it's there. If it's not, the slot is empty. It's nil. Okay? Pretty straightforward. And that doesn't have anything to do with the number of elements that we're accessing. Okay? It's just a standard access table. To delete is pretty easy. Just overwrite the value that was in there with nil. Okay? Now, there are actually different ways of storing this. One way is to store the pointer, okay, x, into the table. So the storage ends up being outside, and the other is to copy the whole record in. And that's an implementation detail that one would have to evaluate in a given circumstance, whether you want the table to be a table of pointers, okay, or to be the records themselves, if you will. Okay? So that's an implementation kit. But in any case, all the operations take order 1 time. Okay? So the problem with this is a great data structure when it works. In fact, there's a related data structure where all you need to know is the presence or absence of a key. And for that, you can use a bit vector. So basically, it's the same array. It's just an array of bits. You just have a bit, which is 1 if it's present and 0 if it's not present. Okay? And I had a friend who was once had somebody come up to him and say, do you know any good disk sorts? Okay, mostly what we're talking about is assuming a flat memory hierarchy. Okay, and although there's a lot of study of algorithms to hierarchical memory, in this class, for the most part, we're going to be just dealing with flat memory, because all it does is it gets more complicated when you go to hierarchical memory. But in any case, disk sorts are more complicated because they've got a different set of constraints. You want to, when you access disk, you can't do random access quite as easily, and when you do access something, you get a big hunk. So he came saying, I have this big disk sort that I need to do. And in querying to find out what actually was needed, it turned out that all he really needed was a bit vector to be able to just set the bits of the keys that were present. Okay? And if he could just set the bits of the keys that were present, then he could just run through the bit vector and print out all the keys in sorted order. Okay? It was sort of like counting sort, where you knew you only had one possible key of every value. And it turns out, and the nice thing about a bit vector is if you have 32-bit words, you get a factor of 32 improvement over the amount of storage required. So the guy didn't even need, it turns out, any disk storage at all. It would all fit in primary memory. But when he was looking at it, he was saying, well, I've got these 32-bit numbers I want to sort. Okay? So this is actually a very convenient data structure and can save an awful lot of work. Not only that, but you can code this up, you can see, in half an hour. I mean, this is with testing. Okay? So it's really. Now, the problem with this method is that the range of keys is usually not so gracious as to be in a finite range for which you would like to set up an array. So for example, your keys may be 64-bit numbers. So how many 64-bit numbers are there? A lot. Right, about, let's see, 2 to the 64th, how about? So how do we estimate that? What's the basic identity used from going from base 2 to base 10? Yeah, 2 to the 10 is 10 cubed, right? So this is equal to 2 to the 4th, which is 16 times, is approximately equal, times 10 to the, why don't somebody raise their hand? Then I don't hear all these little murmurs that I can't hear. All I hear is murmurs. 16, 18, 18. Why is it 18? Okay, so 2 to the 10th is 10 cubes. So therefore, after I've taken out the 16, I've got 60. So I've got 6 2 to the 10ths. Each of those is 10 cubed. That's 10 to the 18th. That's a big number. That's, let me just think if I remember. So does anybody know the prefixes? This is almost, so, and actually if you stored, if these were of any size, you know, in other words, you have, say, 100 bytes or something in a record, okay, then you're talking a, what is it called, a yanabyte or something? Is that what it is? Who knows their, so after giga, then it's tera, then it's peta, then it's exa, then it's yada, and then it's, so yada is what it is. Is that what, is this yada? Is this yada? Well, so this is, no, this is big, okay, big number, okay, and I doubt your computer has that much storage. Okay, just initializing it would be a big effort, okay, to all nils. Okay, make an empty table. Goodbye. Okay, goodbye. Even your virtual memory isn't this big. This is huge. Okay, and then if you have character strings, Okay, I mean, how long is a character? How many different character strings are there of any reasonable length, like people's names or something? Huge. Okay, even though the number of such things is relatively small. Okay, so the solution is a very old idea, and that is to use a hash function h to map the keys into 0, 1, m minus 1. And so one way to look at this is we have here a universe of keys. Let's call it U of keys. This is all possible keys, all 64-bit keys, for example. Okay? And then there's the much smaller set of keys that we care about. We've called that K, right? K. Here's K. And what the hash function is going to do is it's going to take a point here and essentially map it. If I take a look at my table over here, okay, if I take a look at my table over here, so this is T running from 0 to m minus 1. It takes any key here, which I'm drawing as a dot, okay, and it maps it to a given slot. Okay, so we might have one mapped to here, okay, and we might have another one mapped. So this is basically, if this is K1, then this thing is h of K1. Okay, this slot number is h of K1. We apply the hash function, gives us a number in this range, and we just go and put it in that slot. Okay, it can be a much smaller slot, so that if T is can be much smaller than the set of all universe of all keys, it only has to be proportional to K. So here's another one that I'll map to somewhere, K2. Okay, another one, K3. Okay, another one, K4. And another one, K5. And then what happened here? Oops. This is a slot for which, what is it, K3 is equal to h of K5. Okay? And this event, when it occurs, is called a collision. Okay? So that's bad. And most hashing methods, hash table methods, worry about how do you deal with collisions. Okay? So when a record to be inserted maps to an already occupied slot, a collision occurs. Okay? And so the scheme, although clever, doesn't necessarily work without some modification. Okay? So the basic scheme is, oh, that's pretty straightforward, except then you get collisions. Okay? Now we're going to talk on Wednesday about perfect hashing. In perfect hashing, you hash with no collisions. Okay? And so you can always access things in constant time, worst case. Okay? But today we're going to talk about simpler mechanisms to get going. And probably the most popular method for resolving collisions is to use what's called chaining. Okay? And the simple idea is it's okay if multiple things go in the same slot. we'll just link them together into a chain. Okay, we all know how linked lists work. So records in the same slot are linked into a list. So for example, here's a table, and here's some slot I. Okay, I might have a bunch of elements that are all linked into a linked list. And I put the elements 49 and 86 and 52 all in the same list because my hash of 49 was equal to my hash of 86, which was equal to my hash of 52, which was equal to I, right? Because it's the ith slot. Okay? That's what the definition is. Okay? It's also, just in terms of quizmanship, if I say it's equal to something and I look on this board, what else is there to pick but I? Everything else has been taken. Okay? Good. So this is the most popular method by far, okay, for hashing when you're in a single level of the memory hierarchy. And one of the reasons is because it's easy and it works well. Okay. So let's analyze this. Whoops. Okay. Oh, first, before we do the average case, I want to do the average case. What's the worst case of this? New people, new people, new people, new person. Good.
Linear, if everything manages to get chained in like the same slot of hash function.
Yeah. So if somehow the set of keys, the hash function, they all happen to map to the same slot. Okay, then all you have is a big table with a linked list. And so inserting into that linked list, well, maybe that's fast, but then searching it will be slow. Or if you keep it a sorted linked list, then the insertion may be slow. You know, so there are a variety of ways of keeping it, but in any case, it's going to be slow because it's nothing more than a linked list. Okay? So the worst case is not very interesting because we've gone through a lot of trouble to build something that's no better than a linked list if they all end up in the same bucket. Okay, so our hope is, okay, that that's not going to happen. Okay, so in the average case, okay, to analyze it, we're going to make the assumption of what's called simple uniform hashing. Okay, and this is an assumption for analysis purposes because in practice we can't guarantee that the set of keys isn't going to all be guaranteed. We're hoping we're going to have a hash function that has this behavior. But I can't really pick any hash function that'll do it because any hash function I pick, there's always going to be a set of keys that you can pick that are going to all, you know, I just look at what are all the keys that hash to slot I, and I present those as input, and your hash function does lousy. Okay? So we're going to assume that that's not going on, and instead make this assumption. And what that assumption is that each key in K is equally likely to be hashed to any slot in T independent of where other keys are hashed. Because our goal, This is a very common thing that we do in theory, by the way, which is I want to analyze chaining. I don't want to analyze hash functions at this moment. We'll take a look again at analyzing hash function, what are good hash functions. But I'm interested in analyzing chaining, not the hash function. So therefore, I pick an ideal hash function, if you will, okay, one that has this property, okay, in order to do the analysis of chaining and separate the discussion of hash functions for a later thing. And that will give us an understanding of what chaining is all about, okay, as opposed to giving us an understanding only of, or being prohibited from understanding it because we can't pick a hash function ever that has this property, okay, that makes this guaranteed. Does everybody follow? So this is a very common technique to sort of split apart the issues and focus now, right now, on the analysis of the chaining part of it, as opposed to the analysis of the hash function part of it. Okay? So let's see. So we have, we're going to have n keys and m slots in our analysis. And one of the things that's going to be interesting to talk about throughout our discussion of hashing is what's sometimes called the load factor of the hash table. And that's simply n over m. And why is that an interesting number? What is that number in English? Yes, the average number of keys per slot. Okay, so that's a very natural number because that's what we're hoping to achieve generally when we search. We would like not to have to look at order n as we would if they all hashed to the same place as we discussed for the worst case analysis. We would like it to be closer to n over m. Okay. So let's take a look at the expected search cost. Okay. So this one can almost go right from the top. So how much time is it going to take on average to search for a key? Actually, you can distinguish two cases. The successful searches, we're searching for a key in the table, and the unsuccessful ones. We're going to look at the worst case of those. The book distinguishes those and comes up with bounds, separate bounds for each. But it's not really that significant what the difference is in the bounds. Okay? It's much more the worst case of successful versus unsuccessful is pretty much the same. So what is the expected search cost here? This is pretty straightforward piece of linearity of expectation and all. Okay, write down the answer immediately. Alpha, I heard somebody say. That's close. Okay, that's close. In other words, after all, each slot has a list of length on average alpha. So if I'm searching for something at random, that's pretty much what I'm going to have to search on average. Okay, that's part of the answer, but not quite accurate enough. Okay, because alpha could be, so is the search time going to be proportional to 1 over m if n is equal to 1? No. So alpha isn't quite accurate. Yeah?
You have to account for looking up the index.
Yeah, you have to account for applying the hash function and looking up the index. And how much time does that cost? Constant. So it's basically theta 1 plus alpha. So alpha was right. I mean, intuition, right on. Absolutely. Okay, this is what we generally care about, but we got to remember that it's this too, so that it's sort of lower bounds how expensive it could be. And this cost here is basically to hash and access the slot. That's the one. And this part here is to search the list. Okay? And so this cost is equal to theta 1 if alpha is equal to O of 1. So if for example, if the load factor is very high, then the cost is going to be very high. For example, suppose that n is equal to m squared, then the cost is going to be on average about m, because there'll be m elements per slot. Okay? So, but if the load factor, if alpha is equal to order 1, okay, then the cost is order 1. Okay? And this is also equivalent to if n is order m. It's bounded above by order m. So if the number of keys is linear in the size of the hash table, so it tells you how you should size a hash table. How should you size a hash table? Make it proportional to the number of things you're going to put into the hash table. Okay? In a few weeks, we'll cover what happens when you don't know how many elements you're going to put into the hash table. Okay? Because if, I don't know how many elements, I have a hash table, but, maybe it'll be a big hash table, maybe a little. Okay, so in a few weeks, we'll cover how you handle that situation. But right now, the basic idea is your hash table should be about as big as the number of keys in it. Now, you have to, this is where some tuning comes in, because it may be that it should be less than m. It may be that your machine is capable of searching down a list very quickly, and so therefore it makes sense to have several items in a list as opposed to having half of the elements empty. Okay, you have to tune that if you're after performance. Another issue is how much space you're willing to waste. Okay, do you really want each access to be really, really short because you're going to be looking things up a lot, or are you going to be doing insertions you don't mind going down at the expense of making, so that you can have a smaller hash table? So all those things come into effect when you're actually tuning this for real work. Okay, is that? Just make sure I did this once before where I skipped something. Okay, that's the analysis of chaining. Pretty easy. Okay, on Wednesday things will get more complicated. Okay, today's not so hard. Okay, we'll have another proof at the end, which is thing. Mostly today is learning some techniques and bringing everybody up to speed. So I presume most of you have seen hashing. They teach this in 6001, right? Yes? No? Yes? Vaguely? Seen it somewhere else? Okay, people played around. Okay, if it's new, that's fine too. Okay? Okay, great technique. Okay, because on average, order 1 time to look stuff up. In fact, Richard Stallman, who's Richard Stallman, RMS? Who knows who Stallman is? Yeah. Yeah, he's the GNU guy, the GNU Linux guy, okay? And he's, one of the most amazing hackers ever to come out of this place. He's won a MacArthur Fellowship and so forth. He is one weird bird, okay? But he's a brilliant, brilliant, brilliant coder, and he includes hashing as one of his 5 most important ideas in programming. He says, he has this article on, here are 5 ideas that I use over and over again, and one of the important ones is hashing. Okay, very simple, very powerful. Okay, so this is a big idea. Even though it's simple, it turns out as we study it more deeply, it gets much more complicated. So let's talk about how now that we understand chaining, and chaining works well, let's talk about choosing a hash function. Okay. So there are a couple of things that you would like in a hash function. The first is that you would like, of course, that the hash function should distribute keys uniformly into slots. In other words, it's not usually worthwhile considering a hash function that is going to take your set of keys and map, say, half of them into the first slot, a quarter into the next slot, an eighth into the next slot, and so forth. Okay, that's not a very good hash function because most of the things end up in the first slot. Okay, usually you want it to distribute them across the slots. Now, you may violate that if the distribution, if you know something about your distribution of keys. If you think your distribution of keys is non-uniform, you can adjust for that. Okay, but typically, what you do is try not to do things that are going to be as independent as possible of the keys, and that's the second point. Regularity in the key distribution should not affect this uniformity. Okay? And this is, hard to guarantee for a given hash function, because you want the hash function to be something easy, something simple to do. Okay, the most common hash function that people use in the office is sort people's names by first letter of their last name. That's a hash function. I throw everything into a bin, and I have multiple folders under, L for Lyserson, okay, or D for domain, etc. Okay, I mean, just throw them in there, and then if I need to search, okay, I don't actually do binary search. What do? I know the alphabet, okay? I know where, that S is which letter of the alphabet? Who here has memorized the correspondence? 20, what is it? 19? 19. 19th letter of the alphabet. Okay, well, I know it's somewhere down there, so I just go boom and look for it. Okay? And so that basically gives me constant time access based on a very simple to compute hash function. Okay? But that's actually a pretty bad hash function as far as computers are concerned, because you get into some parts of the country and you discover that, the Z's are huge. And, funny, there aren't too many things in X. Okay? And so, that's okay, but you really don't want the regularity to, any sort of common occurrences in the key distribution to affect, how evenly things get divided. Because then when you search, you're going to be searching through more stuff. So there are a variety of common techniques that are used. And in the following, I'm going to assume that all the values we're hashing are integers. Okay, there are techniques for doing strings as well, but very often, even with a string, you'll compact it down into an integer before you do a hash function, or that will be part of the hash function. So the most common method that you use is what's called the division method. Okay, this is the most common, I think, because it's the simplest to understand. Okay, it's not, in my experience, the best one. Okay, although ones that are, quote, better have their deficiencies, and so it all depends and so forth. Okay, and the basic idea here is that I compute the hash of k to be equal to k mod m. Okay, just take the number mod m. That'll give me a number between 0 and m minus 1. That's my slot. Pretty easy, huh? Okay, that's why it's popular. Okay. However, it turns out there's some concerns, some problems with this method. Okay. In particular, you don't want m to have a small divisor. D, say. Why not? What will happen if I have a small divisor? Let's say the divisor D is 2. What's the problem with that?
0 a lot.
Excuse me?
Hash to 0 a lot, but it's class of multiples of 2. So.
Yeah. Okay, so the issue is this issue of regularity. What type of regular, if I have M has the divisor 2, what's the property of regularity in a key distribution? It's a pretty common property that would cause this hash function not to behave well. Yeah?
Most of your numbers are even.
Like most of your numbers are even. Turns out the numbers you're given are mostly even numbers, say. Okay? So for example, maybe you're keeping dollars and cents. Okay? The cents field is often 0 for a lot of things. Okay? And so then this method is going to what? It's only going to hash to the even slots. Because an even number, mod an even number, is an even number. Okay? So that's a problem. Okay? Worse, okay, is if, okay, sort of an extreme worse is if M is equal to something like 2 to the R. What happens then? What sort of, yeah?
There's not very many slots for a lot of
There's not very many slots. So I can make R big, right? So then there's a lot of slots for keys. Did I not understand your? Okay. So what's the problem with picking M as a power of 2 in this method? What does it mean to take some value mod a power of 2? What's that mean in computer bit manipulation? Mod 2 to, 2 to the R. What does that correspond to if I have a word? So here's a word. Here's my M. Here's my key. 1 0 1 1 0 0 0 1 1 1 0 1 1 0 1 0. So there's a key. Lots of bits. Yeah.
Keep the last R digits.
Yeah, you just keep the last R digit. So for example, if R equals 6, this is my hash function. Okay? So it doesn't depend on all the bits of K. Okay? And since we're keeping things in binary normally in a computer, to have all these bits that you're computing a hash of and only using the low order bits, well, those low order bits may all be 0. Okay, that's common words. Or it may be that there's just a few different numbers down here that you're using. Okay, so that's pretty bogus if you have things as a power of 2. Okay, so conventionally in the division method, the rules of thumb that have arisen to make this a method that is reasonably reliable, and hence its popularity, is you pick M to have what property? I've called on you too many times. Yeah, prime. Okay, prime numbers. And it turns out it's also good not to pick it too close to a power of 2 or 10. Okay? Because then it turns out that it can manipulate the number much less than you would expect it to. You really want in a hash function, you want to take those bits and sort of compute something that's a really good scramble of those bits. Okay, that's what you want to do. Really scramble up those bits. That's the value you want. Okay? And the problem with this is that primes are sometimes finding a prime is inconvenient. You can do it statically, but if you have a dynamic program where you're going to be, where the hash table may be a varying size, now you have to have a prime finding thing. And it's not a big deal, but it's sort of like an annoyance. to have to, find a prime. Okay? So this is a very popular method, but the next method is usually superior in my experience, for most applications. It's called the multiplication method. There are a bunch of different ways of presenting it, so I'm going to try a different way this year than I did last 2 years ago. Okay? So in this method, the main advantage of the multiplication method is it's fast compared to the division. So division is basically a pretty slow operation. It's called the division method because in order to find a mod, you have to do division. Okay? And division is generally slow on most machines, even today. Okay? Most computers, because this is integer division, not floating point. In integer division, most computers have what they call a divide step. They don't actually do a divide. Okay? And they iterate it. Okay? So they have to go into a software loop in order to compute division. They actually have to do the same thing for multiplication. It's just that for multiplication, that's in the inner loop of division. Okay? So you actually, very often for division, you've got a couple of loops going on in order to calculate the reciprocal. There's assists, but generally for integers, I'm always disgusted at how badly multiplication and division have been optimized on most microprocessor chips. And the reason they haven't optimized it is because many times the most common use of multiplication is in array indexing. Okay, and you say, gee, it's being used everywhere. If you do two-dimensional array indexing, you index, it's really stored as a linear array, and you have to find where you are, and that involves a multiplication. But it turns out that most compilers are very good, if you're iterating through an array, a two-dimensional array, they're very good at figuring out how to replace this multiplication by an addition. Okay? And so therefore, you don't actually multiply very often in any of the benchmark codes that people run. And consequently, things like hashing go much slower than they ought to if people in there understood that if you provided it, people would use it more. Okay? It's one of these facts. So the multiplication method works as follows. The modulus is going to be, or the number of slots in our table, sorry, is going to be a power of 2. Here we actually, division method, don't use power of 2. Okay, multiplication method, the easiest multiplication method there is, uses powers of 2. Okay, and this is usually convenient for people. Finding a power of 2 is a lot easier than finding a prime. Okay, it's like set a bit. Okay, so and let's say that our computer has W-bit words. Okay, so then the hash of k is then equal to this expression. Okay, where this a, so it's a times k mod 2 to the w, and this operation is the bitwise right shift operation. Okay, so it takes the bits of the computer word and just slashes them aside. What's the circuit? Does anybody know the circuit that is responsible for doing bitwise right shifts that's used in microprocessors? I'm sure you've heard the term somewhere. Learn more hardware. Hardware is great. Learn hardware. Hardware is fun. Yeah. It's called, well, it's built that way, yeah? So what, but you know what it's called? It's called a barrel shifter. Anybody heard that term? A barrel shifter? Okay, basically a barrel shifter means it can shift any number of positions, whereas an ordinary shifter only shifts one position. Okay, barrel shifter means it'll shift any number of positions. So every microprocessor has a barrel shifter. It can shift by, okay, and in one cycle it can do this operation. Okay? The multiplication is expensive. This a here is an odd integer. In the range 2 to the w minus 1 less than a less than 2 to the w. Okay? So if you want to view it as it's an odd integer with the high bit, not the sign bit, but the high order bit is on, and it's odd, which means the low order bit is on. Okay? So and that's just a constant that we use. And generally, you don't want to pick, the one caution here is you don't pick A too close to 2 to the W. Okay? And this is a fast method because what does it mean to multiply something mod 2 to the W, where that's your word size? Yeah. Yeah. Not quite. So when you multiply two n-bit numbers, excuse me, w-bit numbers, when you multiply two w-bit numbers, how many bits in the product? So, okay, so close, it's 2w. Okay, and you take the last w bits. Okay, good. Okay, so if you multiply two w-bit numbers, the product is going to be, basically the product is the sum of the number of bits. Because number of bits of a number is just what? It's basically its log. Okay, so you're adding the logs. Okay, so let's do an example, and we'll see what this thing actually does. Oh, let me do the example down here. Good. So here's an example. Okay, I'm going to have a huge hash table, and there's 8. Okay, so 8-slot hash table, and an enormous computer with a word size of 7. Okay, so 7 bits per word in my computer. Okay, not even a byte. Okay, but more than a nibble. Okay, so everyone knows a nibble. What's a nibble? Half a byte, right, 4 bits. Good. Okay, so some people I think were laughing because they thought I was making a joke, but a nibble that is what they call a nibble. I didn't make it up. Okay, not my joke. Okay, 101001. So this is going to be my A, and 110111. This is going to be my key K that I'm going to hash. What I'm going to do is multiply those. Anybody have a binary calculator on them? Well, I'm not going to work this out. I'm just going to copy, and if it's wrong, it's your fault. Okay, for not being prepared. Okay, well, I know the low order bit is correct here. Okay, 00110101001. So that's my product. Okay. And so the first thing is that when I multiply two n-bit numbers, I get a 2 n-bit number, and I can just ignore the high order halves, because I'm taking it mod 2 to the 7th. So these just get ignored. And it turns out, conveniently, most computers have an instruction where you can take two w-bit numbers and produce the low order. It'll produce either a 2-word answer or a 1-word answer, which is the low order bits. And if you produce just the low order bits, guess what? It's faster than if you produce all 2n bits. Okay? So that's convenient. Okay? It's actually typically a sequence of instructions. There's what's called a multiply step operator that lets this go with a sequence of instructions. Okay, so this is the result. And now what I do is I right shift by w minus r. So this says I right shift 4. And so what's my hash function here? Which bits am I extracting for the hash function? 011, good. Okay, so this part here is my h of k. And the way they're extracted is I just shift them right, and that basically zeroes those out and moves this down to the right end where it can now be used. It's a very fast operation. Okay, so does everybody see what happened there? Okay, why that's a pretty fast operation? Okay. Okay, let's imagine this a little bit. One way of visualizing what's going on here and why this method actually works well is with what's sometimes called a modular wheel. So let's imagine that I've taken all the integers and spread them around this wheel. If it's a modular wheel, I'm going mod 2 to the w. So that means my 0 point here has 0, which is congruent to 2 to the w, which is congruent to 2 times 2 to the w, which is congruent to 3 times 2 to the w, etc. Mod, all this mod 2 to the w. Okay, so all those are congruent mod 2 to the w. Okay, so I basically run around like this. Okay, and what the result of this is to look at these bits here, okay, which are the high order bits of the lower half. So the high order bits correspond to sectors in this diagram. Okay, so if this is 0, then if I divide it into 8 parts, since I'm taking 3 bits, then a 1 will end up in this position at this point, and a 2 here, and a 3 here, 4, 5, 6, 7. Okay? So if I look at what the end result is going to be when I take my a times k mod whatever, okay, if it falls into this range, it's all going to be 0. If it falls into this range, it's all going to be 1, and so forth. So if we take something like a, so what did I use as a? 101110110001. Okay, so where's that on this wheel? It's like after 5, right? How much after 5? A little more than halfway. Just a touch more than halfway, probably not enough. So that's A. So basically A took me around like this. Okay? Then where's 2A? So 2A is easy to calculate, right? What do? Mod 2 to the w. How do I multiply it by 2 on a computer and hardware? On bit minute. Left shift by 1 bit. Like multiplying by 10, add a 0 at the end. And since it's 2 to the w, I just take that one off. So that left shifted is about where? Where's that going to end up? It's going to be added just beyond 3, right? Okay, so that's 2A. So basically, I'm adding another A as I go around here. Okay? Where's 3A? Where's 3A? Okay, I can get 3A by adding 2A and A. Somebody do that quickly? Yeah, it's about halfway between 0 and 1. Good. Okay, so it's about here. Okay, 3A. Okay? So you see, each time I add another A, so if I say take a key, a random key, and I say, you know, add in, multiply it by so many A's, where does it end up on this wheel? Hard to know without actually doing the multiplication. That's why it's sort of a good one. There's one modification of the multiplication method, which is to actually start out by having a b, which is added in to the result. and once again modding that. Okay? And that way, you don't always start at 0. Because here, notice, 0 always hashes to 0. Okay? So it may be that you want 0 to hash to a random place. So one way to do that is always start from a random place and then add in the A's. Okay? So it's another method that works pretty well if this is not giving as good results as one would like. We're going to talk more about some more sophisticated hash functions, but these are the two that are most commonly used in code, just because they're so easy. Okay? And most of the time, there isn't a big priority if it turns out things take a little bit longer, and it's very unlikely that you're going to exploit the bad features of this and so forth. But sometimes you really care about the quality of your hash. Okay, and then you have to use a more sophisticated method. We'll talk about some of those next time. Okay, I want to talk now, switch gears. So we've talked about collision resolution by chaining, and we've talked about choice of hash functions. I now want to go back to collision resolution to talk about another method for collision resolution called open addressing. So pretty much everything, right now you know pretty much all you need to know to go out and be an average programmer. Okay? Because you know about hashing. Okay? All average programmers know about hashing. Okay? So you're average programmer. Okay? We're now going to start to teach you the things that let you be an above average programmer. Okay? Hopefully. Okay? But part of this is up to you, too. I mean, I can teach it, but you folks have to learn it. Okay? So in open addressing, it's a different way of resolving collisions, and it's featured by the fact that there's no storage outside of the hash table. So you actually store everything into the hash table, put a copy of the record right in the hash table, and you don't use any storage outside of it. And the idea here is that when you hash something into the table, you probe, as they call it, systematically until an empty slot is found. So the idea is you hash to a location in the table. If the table if the slot is empty, you just put it there. But if you have a collision, no problem, you hash again. Okay, slightly differently. Okay? And then you check there. And you keep doing that till you find an empty slot, and that's where you put it. Okay? So the hash function for this type of operation maps our universe of keys here, U, cross, and now we have another component. It's a 2-argument hash function, which is the second argument being the probe number. Okay? Which probe? The 0th probe, the first probe, the second probe. Okay? So this is the probe number, probe index, whatever. And it maps that into a slot. Okay? So I take, for each probe, okay, so what's a basic property that I should have of this probe sequence to make it this a reasonably non-dumb method? Sure.
Permutation of the probe number on the left.
Good. It should be a permutation. Okay. Actually, it should be a permutation of the slots. Okay. In other words, I probe a different slot every time I probe. If I pick a hash function which continually probes the same place, I'm not going to make much progress. Continually probes something I've said. So every time I want a different one. So this probe sequence for a given key should be a permutation. Okay? Probe sequence for a given key should be a permutation so that we're not checking where we checked before. That's common sense. Okay. Now, another thing about open addressing is, since there's no storage outside of the hash table, and this doesn't happen with chaining, the table may fill up. Okay? So unlike chaining, it just gets slow. You have a little hash table and lots of items. Chasing down all those pointers, it just gets slow. But in open addressing, the table may fill up. And so I've got to have a table that's big enough to hold my items. Also, it turns out that deletion is difficult in such a table. Okay, it can be done, but it's a tricky business to do deletion. So typically, open addressed hash tables are used for things where deletion is not going to be much of a you're not going to be doing deletion. Okay, so you may want a fixed hash table that I just fill up with a bunch of things. Okay, so for example, compiler, where maybe all I'm doing is adding symbols. I'm not ever taking symbols away, for example. Okay, might use an open addressed hash table. So let me give you an example of how this works to make sure that these ideas are solid in your head, and then we'll look at some probing strategies and some analysis. Whoops. I'm doing this today all the time. I finish with the front board, and then instead of going to the back board, I decide I'm going to go to the other board. Okay, so here's an example of insert. Okay, so let's say we're inserting a key which is 496. I always liked 496 because that's a perfect number. Okay, people know what perfect numbers are? Okay, so this is number theory. So it's a number, if you take all the divisors of 496 that are less than or equal to itself and add it up, you get 496. How about that? Okay, amazing. Okay, so there are two numbers smaller. Okay, one of them is 6. Okay, 1 plus 2 plus 3 equals 6. Okay, and the other one is 28. Okay, and then they're a bunch bigger. But this is the third one. Okay, so let's have our table here. And let's say our table has got some numbers stored in it, 586 and 133 and 204 and 481. Okay, and I'm going to insert 496 into this table. So the first thing I do is I probe whatever my hash is of 496, and it's my 0th probe, so therefore 0. Okay, and I might look at, that may go to say 204 and I get a collision. So I say, okay, that one's full. So let me try to probe, do another probe, h of 496, comma 1. And that might go up to 586. Another collision. Oh, that's no good. And so then the next one I do is I probe h of 496, comma 2. And let's say that goes to here. And I say, yay, yippee. Okay, and so then I insert 496 here. And that's where 496 goes. Okay, so to search, okay, we basically go through the same probe sequence. And this is why deletion is hard. Okay, although it can be done, there are mechanisms to make it work. Because if I deleted something, then I'd think, oh, it wasn't in the table because I came across nil. So if it's a successful search, then I'll find the record. Because I'll keep hitting the same collisions I hit. If there are no deletions, I'll keep hitting the same collisions I had as going in, okay, until I actually get to the record. Okay, because I'm going through exactly the same things. Okay? If it's unsuccessful, okay, I'll find a nil. So typically, in an open addressed hash table, to simplify the end termination, we don't let it be completely full. We always make sure there's at least one empty slot in the table. And that way, if there is no space, we'll find it. Okay? I'll find nil. I basically go over and it won't be there. Okay? Is that pretty straightforward, how open addressing works? So basically, by repeating the same behavior when I'm searching, okay, as when I insert it, I'll find it. There are a variety of different probing strategies that are used. By far, the most common is the worst. Okay? And sometimes it's okay, but it really is, for the amount of work that it's okay. So the first one is linear programming, linear probing. Okay? And basically here what you do is you simply look sequentially through the table. Okay? So the idea here is, okay, and in the notes and in the book there's a formula, but basically in linear programming, in linear probing, okay, when I probe here, if it was occupied, then I check the next slot. Okay, and if it's empty, I put it in. Otherwise, I check the next one. And so the sequence is just basically a rotation of the numbers from 0 to m-1. Now, the problem with linear probing is that a phenomenon called primary clustering occurs. Okay, where basically you get long runs of filled slots. So if you think about it, the odds that this slot will be filled, okay, by a random insertion is greater than the odds that this one will be filled, because this one will be filled if any of these 4 hit in linear probing, whereas this one will only be filled if it's a direct hit. Okay? And so notice what happens when this one fills. Okay? It now changes the odds, and so basically you get a long run of filled entries, and those long runs tend to encourage more that run to increase in length. And so you get these blocks around in your code with very few things in between. So it's a very uneven distribution. You get clustering. Okay? So this is basically not a very good method. It can work. It's not a bad method. I wouldn't present it if it were completely bad. But the advantage is that the hash function is very simple to compute. You just simply look, and then you just keep adding 1. So there's another strategy that is probably the preferred method, okay, called double hashing. And for this, we let h of ki be h1 of k plus I times h2 of k mod m. Okay? And so what this is saying is I is initially 0, so I just compute an ordinary hash function of 1 argument, just hash the value. And then if that is filled, then what I do is I add in h2 of k, some other hash function. I add to it mod m, everything mod m. And then if that's filled, then I just keep adding in h2 of k. So rather than adding 1 every time, I always just add in h2 of k. Okay, and so therefore I have to compute 2 hashes. Okay, but I only have to compute 2 if I'm going to at least 2 slots. Okay, and I then just have to do additions for the later slots. Okay, so it's a fairly simple operation, additions mod m. Okay, so this is an excellent method. Okay, and usually you pick m equals 2 to the r and h sub 2 of k to be something that's always odd, and that way you guarantee that you have the property that it's a permutation, because then this thing is relatively prime to the size of your table. So it's a very, very effective method. Okay. The analysis for open addressing is only a little bit more complicated. Well, I mean I guess it's a little more complicated as opposed to only a little bit more complicated. It's more complicated than for chaining. Okay. So for this, we make an assumption of uniform hashing, as it's called, which is a generalization of the simple uniform hashing we had before. And the idea here is we're going to assume each key is equally likely to have any one of the m factorial permutations as its probe sequence. Okay? And that's independent of the other keys. Okay? So basically it's a generalization. We want to understand what does open addressing mean, not what do particular hash functions mean. So this is a generalization, okay, of sort of this would be the perfect hash function if you had it, okay, and you could compute it. So the theorem that we're going to prove, it's always nice to have a lecture where we have a theorem, okay, because this is a joint class with course 18. Okay, so got to not only do math, you got to prove theorems, okay. So, and that is the expected number of probes is less than or equal to 1 over 1 minus alpha, if alpha is less than 1, which is to say if n is less than m. Okay, so number of probes is 1 over 1 minus alpha. And the proof, so I'm going to give sort of a little bit of a informal proof here. And then we'll do the math, which is formal, but the justification is a little bit informal. I mean, technically, you ought to do this more carefully as the book does, but I don't have time to do that in lecture. So let me give you the intuition of the proof. Okay? So everybody understand what this says? Expected number of probes, 1 over 1 minus the load factor. Remember, the load factor is always less than 1 because we have fewer elements in our table than this number of slots in the table. Okay? So the first thing is 1 probe is always necessary. Okay? And with 1 probe, so, okay, and for that 1 probe, with probability, I've got prob and probe here, n over m, so with probability n over m, I have a collision. Because there are n elements in my table. Okay, so if I probe, okay, and I'm looking for a place to put this inserted element, okay, with probability n over m, there's a collision because there are n things in the table and there are m slots, and so that's the fraction. Okay? And that implies that a second probe is necessary. Okay, so we go on to the second probe. And then with probability, so what's the probability I get a collision on the second probe? N over m minus 1? N minus 1 over m. What did somebody say?
N over m minus 1.
Who's saying this? Yes, what is it?
N over m minus 1.
N over m minus 1. n minus 1 over m minus 1. Good. So you're all in the right ballpark, okay? Okay, because I'm only looking at the slot that wasn't filled. I've removed a slot that was filled, so I'm removing both the slot and an element, okay, from the rest. Okay? So then I get a collision implying a third probe is necessary. Okay? Okay? So, and then we keep doing this, right? And what would, then be n minus 2 over m minus 2 and so forth. Everybody gets the drift. Okay? So let's just make a note here, because this is that n minus I over m minus I, what's the relation of that to n over m? For I equals less than. Why less than? Yeah, that's doing it the hard way. Yeah, I can multiply and then, and then my mind goes blinkers because I've got the less than and I've got the ratios and I've got the minuses and I'm flipping signs and I get lost. So how do I know that when I've written this that it's right? Got to think about these things. So you do sanity checks. So when you get this from doing that, you know it's right and not wrong. How do I do that? Yeah.
Well, if I were m, or n minus I over n minus I would be 0.
Yeah, so that would be less. That's one way. Another way to think of it just generally is that since the numerator is smaller than the denominator is bigger, then if I'm subtracting the same amount from each, I'm affecting the numerator fractionally much more than the denominator. Okay, and this is alpha, right? Okay, so we have just the last equation of the proof, and then we're done, which is the expected number of probes is therefore 1 plus with probability n over m. It's going to be 1 plus with probability n minus 1 over m minus 1, 1 plus n minus 2 over m minus 2. Okay, dot, dot, dot. This is why it's not also very rigorous. I don't like dot, dot, dots, but sometimes they're helpful to understand things. I think I even have my parentheses balanced. Okay? So that's basically just writing out what we set up there. Okay? And that's less than or equal to 1 plus, well, that's just alpha. 1 plus, well, that's less than alpha. 1 plus, well, that's less than alpha. Dot, dot, dot. And this is less than alpha. Dot, dot, dot. Okay? Well, that's less than or equal to, basically, I'm going to just take the whole inner part to infinity and multiply it through. I get 1 plus alpha squared plus alpha cubed plus, etc. Infinite series. Okay? That's just summation of I equals 0 to infinity of alpha to the I. And we all know that that's equal to 1 over 1 minus alpha, because it's a geometric series. QED. Okay, so this runs in constant time when? Okay, homework. Okay, exercise. When does that run in constant time? You can look it up in the book, but you can also think about it. So hashing's great stuff. We'll see more and really interesting stuff, i.e. hard stuff, also on Wednesday.